Welcome back, learners. We are discussing here about the catalyst and catalysis. As I told you in the previous part, catalysis is a chemical reaction which is brought about by the catalyst, or catalysis is a phenomena which takes place through the catalyst. Catalysts are a chemical substance which increase the rate of reaction or decreases the activation energy. And how the decreases the activation energy? By providing a different pathway. In this part we will discuss catalysis in organic reactions, different types of catalysis, nucleophilic catalysis, acid catalysis, and iodine based ion catalyzed reactions, base catalyst, metal ion catalyst, Tolman catalytic reactions, and Wilkinson catalyst. As I told you in the previous lecture, in the catalytic cycle, the number of turn through the catalytic cycle before the catalyst becomes deactivated called turnover number, that is TON. So, the TON is moles of the reactant divided by the moles of the catalyst and the yield of the product. Now, catalysis in organic reactions. The compound, organic compound especially, act as a catalyst. Example, biomolecules. Some of the biomolecules act as a catalyst. Proline, phenylalanine, these are the amino acids, and oligopeptides. They can also act as a organic catalyst. And a small molecule that catalyze the reaction in absence of metal or metal ions. These are the organocatalysts. There are two types of organocatalysts, that is covalent and non-covalent catalyst, that are having a covalent bond, and another type is non-covalent organocatalyst. Organocatalysis is the form of catalysis in which the rate of a chemical reaction is increased by an organic catalyst, and this organocatalyst consists of carbon, hydrogen, sulfur and other non-metal elements found in the organic compounds. These organocatalysts are important in green chemistry due to mild reaction conditions, and these organocatalysts are eco-friendly catalysts that can be used in the many organic reactions like water and sulfur, critical carbon dioxide, supercritical carbon dioxide can act as a organocatalyst and used in green chemistry as a green solvents. So, these are the organocatalysts. Earlier in 1990s, only enzymes and metal catalysts were used in the asymmetric synthetic. What are asymmetric synthesis, learners? Asymmetric synthesis are stereoselective synthesis in many pharmaceutical industries using asymmetric synthesis. So, earlier 1990s, only the enzymes and metal catalysts were used in the preparation of asymmetric synthesis, that were biological catalyst, organometallic catalyst and organic catalyst. That is, that organocatalyst increase the rate of reactions. So, the organocatalysts are less toxic, less polluting, more economically than organometallic catalysts that dominate in asymmetric synthesis in earlier 1990s. Some most common catalysts are, we are talking about the organocatalysts. So, some most common organocatalysts are nucleophilic catalyst, acid catalyst, base catalyst and metal ion catalyst, and these catalysts provide an energetically more favorable pathway for organic reactions. Now, we will discuss about the nucleophilic catalyst. What is the role of nucleophilic catalyst, learners? Nucleophilic catalyst increase the rate of reaction by acting as a nucleophile in the form of an intermediate by forming a covalent bond with one of the reactant, and these nucleophilic catalysts are also called covalent catalyst. On your screen you can see the example. Here this alkyl halide react with nucleophile, that is here iodide ion, and the reaction takes place with OH. The iodide ion, when we use the iodide ion, it increase the rate of reaction and convert that ethyl chloride into ethyl alcohol. So here by adding the iodide ion, which act as a nucleophilic catalyst, increase the rate of reaction, speed up the rate of reaction, and we get a alcohol. So here that iodine ion act as a nucleophilic catalyst. Now if the same reactions, what happen when the same reaction takes place in absence of that iodide ion, which is a nucleophilic catalyst. So in absence of iodide ion, ethyl chloride is converted into alcohol in one step. So learners understand here, when the reaction takes place in absence of that nucleophilic catalyst, we get a SN2 reaction, and the reaction is one step reactions. Although we are getting here alcohol, but when we use iodide ion as a nucleophilic catalyst, we get a alcohol in two steps. So there is a two-step reaction. The iodide ion react with that ethyl chloride two former, again ethyl iodide, then ethyl iodide react with OH, we get a alcohol. So in this way we can increase the rate of reaction. The equilibrium reaches earlier by using that nucleophilic catalyst. So the first SN2 reaction in the catalyzed reaction is faster than the uncatalyzed reaction, because in protic solvent iodide ion is better nucleophile than the hydroxide ion, which is nucleophile in uncatalyzed reactions. So hydroxide ion, we have seen in the previous slide, the hydroxide ion act as a nucleophile in absence of iodide ion, but when we add iodide ion in same reaction in protic solvent, iodide ion act as a nucleophile because it is a good leaving group. So in second SN2 reaction, which is catalyzed reaction, which is the faster reaction than the uncatalyzed reaction, because iodide ion is a weaker base, and always remember, weaker base are always better leaving group. So important point to learn here is iodide ion increase the rate of formation of ethanol by changing a relatively slow one-step reaction to fast step reactions. Another important example you can see on your screen, imidazole. Imidazole is a nucleophilic catalyst, and when we used in hydrolysis of phenyl acetate, this is the on your screen you can see hydrolysis of phenyl acetate. So when hydrolysis of phenyl acetates takes place in presence of a nucleophilic catalyst, which is here you can say, you are looking here, imidazole. Imidazole catalyst provide favorable pathway, and we get desired product over here. So imidazole is a better nucleophile than the water, react faster with ester, hydrolyzed much more rapidly, and increase the overall rate of reaction. So when rate of reaction is increased, it means that the reaction is completed in a less time. No energy is required, less energy is required during the reactions. Now acid catalyst. Another important type of organocatalyst are acid catalyst. Acid catalyst increase the rate of reactions. How they increase the rate of reaction? By donating a proton to the reactant. because acids, Lewis acids having a pair of electrons. So that acids donate a proton to the reactant. So it is a acid catalyzed hydrolysis of ester. You can see on your screen, acid catalyzed hydrolysis of on ester, we get acid and alcohol. So here this is a mechanism how we get esters in presence of acid catalyst. So you can see the carbonyl protonation takes place on carbonyl carbon. That carbonyl carbon is then having a hydrogen. This is protonated oxygen. Then it react with water and we get a finally alcohol and acids. So it was the here mechanism of acid catalyzed hydrolysis of ester in previous slides. So what happened here when the hydrolysis of ester takes place in presence of acid catalyst? What happened here? The formation of tetrahedral intermediate takes place and again collapse of that tetrahedral complex takes place. These are the two slow steps. So catalyst, that acid what is the role of that acid catalyst in the reaction? So learn that acid catalyst increase the rate of that about two slow steps, right? So because increasing the rate of first step will not increasing the rate of overall reactions. So the acid increases the rate of both slow steps of this reaction, formation of tetrahedral complexes and collapsing of tetrahedral complexes. So that both steps rate is increased by using the acid catalyst. So increase the rate of formation of tetrahedral complex or tetrahedral intermediate here, promoting carbonyl oxygen. It is called specific acid catalysis because the proton is fully transferred to the reactant before the slow step of the reaction begin. This is mechanism of specific acid catalyzed attack by water on carbonyl oxygen. So here nucleophile attack a fully protonated carbon. On your screen you can see here. This is an example of acid catalyzed attack by water on carbonyl group, protonated carbonyl group. So the here nucleophile attack on the protonated carbon and finally formation of a desired product. So this is another example of specific acid catalyzed elimination of leaving groups takes place. So these are the different steps by using of acid catalyst. Now it is a general acid catalyzed elimination takes place. So how the leaving group eliminate over here? Collapse of the tetrahedral intermediate, the leaving group picks up a proton and quickly eliminated from the reactions, right? So it is a general acid catalyzed elimination of a leaving groups. Learners, another important organic catalyst are base catalyst or base catalysis. So base catalyst, as the acid catalyst increase the rate of reaction, base catalyst is also increase the rate of reaction by removing a proton. So we have seen the acid catalyst increase the rate of reaction by donating a pair of electrons, right? But here the base catalyst increase the rate of reaction by removing a proton. So that is the difference between both of them. So by providing the pathway with more stable intermediate ion, the proton is removed from the reactant in base catalyzed reactions. So you can see on your screen the transition state for elimination of OH from a negatively charged tetrahedral intermediate and elimination of again over here neutral tetrahedral intermediates. So the proton is removed from the reactant is in a base catalyzed reactions. Another important catalyst is used nowadays is metal ion catalyst, or metal ion catalyst also called electrostatic catalyst. So these are the catalyst. Here what is the characteristic of these catalyst? Learners, metal bound with water and increase the acidity of water to form a metal hydroxide ion. So, the metals exert their catalytic effect by coordinating with atoms that have a lone pair of electrons. How the metals that bound to the reactants. So, the feature is that metals coordinate with the atom which are having a lone pair of electrons, metal, because everybody knows, all of you knows, all metals are electropositive in nature, right. So, it coordinate with the atoms which are having a lone pair of electrons. So, the Lewis base having a lone pair of electrons, it coordinate with the metal ion. So, this is the example of catalyzed by liver that is liver enzymes, that is alcohol dehydrogenase. So, here zinc ion stabilize the negative charge on the oxygen. Similarly, we can see that metal catalyst act as a electrophilic catalyst, may generate nucleophile, which is key feature to increase the acidity of nearby molecules, and also bind the substrate. So, during the binding of the substrate, the binding energy is more. When metal bind with the substrate, we have seen there the binding energy is more. So, due to that more binding energy, that metal easily bind to the substrate. So, in this example, you can see here, this is a ester, and the reaction takes place in presence of CO2 plus, that is cobalt, which is a metal, and that metal catalyzes the esters, ethyl esters, and that ethyl esters converted to glycine, and finally we get a ethyl ester of glycyl glycine. So, here cobalt metal act as a metal ion catalyst over here, or electrostatic catalyst. Now, on your screen you can see the coordination, how the coordination of metal ions. So, you can see here the coordination of metal ion with carbonyl oxygen makes the carbonyl group more susceptible to the nucleophilic attack, and due to that it stabilizes the developing negative charge on the oxygen in transition state. An important feature of metal ion catalyst are they make a reaction center more susceptible to the receiving electrons, make a leaving group weaker base, and also increase the rate of reactions. Now, what are intermolecular reactions? Learners, rate of any chemical reaction is determined by number of collisions, because when the reaction takes place, the collision takes place between the molecules. So, the rate of chemical reaction is determined by the number of collisions between the two molecules with sufficient energy and with a proper orientation in a given period of times. Now, how the rate of reaction calculated? The rate of reaction is calculated by number of collision divided by unit of time multiplied by fraction of sufficient energy into fraction with proper orientation. So, this is the formula by which we can calculate the rate of reactions. Reason, what is the reason? Because the catalyst decreases the energy barrier of the reaction, because when we add catalyst in any chemical reaction, it decreases the energy barrier of the reaction and increase the reaction rate by increasing the fraction of collisions that occur with sufficient energy to more come the barrier. So, intermolecular reactions are first order reactions, while intermolecular reactions are the second order reactions, and the relative rate is determined by first order rate constant divided by second order rate constant. So, that is the rate. How can we calculate the relative rate? It is a first order rate constant divided by second order rate constant, and the unit is m. M is called reflective molarity, and the concentration of the reactant that would be required in an intermolecular reaction for it to have the same rate as the intramolecular reactions have. It's very important point. Now, what are the intramolecular catalysis? We have discussed, we have seen there what are the intramolecular reaction and how we can calculate the rate, reaction rate. Now, we will discuss here what are intramolecular catalysis. When a catalyst is a part of reacting molecule, intramolecular nucleophilic catalysis, intramolecular general acid or general base catalysis, and intramolecular metal ion catalysis, also known as intramolecular catalyst, also known as anchimeric assistance. This is the example of intramolecular base catalysis. So, you can see intramolecular means the reaction takes place within the molecule. So, on your screen you can see how the reaction takes place within the molecules and how the oxygen takes part in the reactions. The one proton from adjacent carbon, which is our having carbonyl carbon, is participate in the reactions. So, it is an example of intramolecular base catalysis. Another example is intramolecular general base catalysis. So, here the reaction takes place within the molecule because H from the carbonyl here that is having carbonyl carbon is have proton is removed from there. So, due to removal of proton, we get a double bond here. So, it is a intramolecular general base catalysis. This is an example here, intramolecular metal ion catalysis, hydrolysis of ester which is catalyzed by nickel ion. So, metal ion complex with oxygen and nitrogen of the reactant as well as with water molecules. Metal ion increases the rate of reaction by positioning the water molecule and making it a stronger acid which increase its nucleophilicity. So, this is also important example where we can say how the reaction takes place. So, it is a chlorocyclohexane when react with aqueous solution of ethanol to formation of two products, and there are two products formed because there are two nucleophile, one is water and one is ethanol. So, in the solution there is two nucleophile, one is water and ethanol. So, here we get a two products. Similarly, hydrolysis of phenyl acetate increase 150 fold at neutral pH in presence of carboxylation in ortho position. So, when carboxylation takes place at ortho position, the rate of reaction increased. Another example is over here. Here you can see in the structure the intramolecular general base catalyst increase the nucleophilicity of water, increase the rate of reactions. Similarly, some important example of that catalyst. One important example is hydrogenation of alkenes using Wilkinson catalyst. So, Wilkinson catalyst is a very important catalyst, and in hydrogenation of alkenes we use the Wilkinson catalyst. What is the Wilkinson catalyst? Learners, Wilkinson catalyst is a chloride tries rhodium 1, that is RHCl pH3 whole thrice, and it is red brown colored solid which is used to catalyze the hydrogenation of olefins with molecular hydrogen. So, it acts as a homogeneous catalyst. So, same phase as a substituent. So, it is having the same phase. So, Wilkinson catalyst is a very important catalyst used in hydrogenation of alkenes. So it is the structure of Wilkinson catalyst. RH, which is a rhodium and which is a metal. So that metal is attached with 3 triphenylalanine. Another example is where we have to use the catalyst is that palladium or nickel. So learners, nickel, copper, palladium or platinum are heterogeneous catalysts deposited on an intersolid support like alumina. So that deposit on the support, and here this is hydrogenation of alkene. In hydrogenation of alkenes, when metal catalyst used, it is a thermodynamically favored reaction, but does not takes place at room temperature and room pressure. So the hydrogenation of alkenes in presence of metal catalyst cannot takes place at room temperature or pressure. We need slightly high temperature, and although it is a thermodynamically favored reactions. Another important example where Wilkinson catalyst involved is catalytic in this reaction, the oxidative addition of H2 to 16 electron RH first complex. So this is again Wilkinson catalyst. So here the RH, that is rhodium 2, it is 18 electron rhodium 2 dihydro complex, and you can see if we talk about that complex geometry, it is a square planar. So during the reaction, square planar geometry changed to octahedral geometry during the oxidative hydrogenation of alkenes. So removal of PPH3 and hydrogenation of that alkenes takes place. So 18 electron to 16 electrons. Learners, catalytic cycle reaction. What is catalytic cycle reaction or Tolman catalytic loop? What is this? Learners, this complex, that rhodium based complex, interact with the alkene, hydrogen transfer from 1 to migratory insertion, 16 electron alkenes complex to form an octahedral complex, then hydrogen migrated to the carbon, reductive elimination of alkenes, and catalyst re-enters the catalytic cycle. So this is the Tolman catalytic loop. Now what is the features of Wilkinson catalyst? You must know what is the features. Wilkinson catalyst, here using the Wilkinson catalyst, rate of hydrogenation of terminal alkyne is greater than the terminal alkenes. So you can see the difference, alkynes and alkenes. In case of alkynes, when use the Wilkinson catalyst, the rate of hydrogenation is greater, right? So again, the rate of hydrogenation of conjugated diene is slower than the isolated dienes. So that's this same catalyst, when we used in hydrogenation of conjugated diene, the rate is high. Steric hindrance decreases the rate of hydrogenation. So in case of cis alkene, which is greater than the trans alkenes, so more number of alkyl groups, the rate of hydrogenation is decreases. So you must remember, as the number of alkyl group is increases in the alkenes, the rate of hydrogenation is decreases. So the if compound contains 2 or more double bonds, the least hindered double bond are reduced, and the Wilkinson catalyst is selective for hydrogenation of carbon-carbon double bond that are not sterically hindered. So here this is asymmetrical hydrogenation when chiral chelating phosphine ligands are used in place of triphenyl phosphine in Wilkinson catalyst. So it is used to synthesize optically active compounds, especially asymmetric hydrogenation, and used in pharmaceutical synthesis. So it was about the catalyst or catalysis, and we had discussed acid catalyst, base catalyst, metal ion catalysis, and how the reaction takes place with catalyst and without a catalyst. Also, we in the last few slides we had discussed about the applications of catalyst, and in that case we had discussed Wilkinson catalyst. Thank you.